A dot b represents the dot product of the two vectors a and b, and it is equal to the magnitude of a times magnitude of b times cosine theta. To understand this relationship, we need to first understand the definition of the dot product. Consider these two vectors, a and b. If vector a has a total of n components, and each of these components are represented by the numbers a1, a2, a3, all the way up to an, and vector b is given by b1, b2, b3, all the way up to bn, then a dot b is found by multiplying the first component of a by the first component of b, then multiplying the second component of a by the second component of b, and so on, and then adding together all the products. That means a dot b equals a1 times b1 plus a2 times b2 plus a3 times b3, and all the way up to the very last component, an times bn. Using sigma notation, the definition of the dot product becomes this, which can be read as the sum of ai bi as I goes from 1 to n, where I is a natural number. So for example, if vector a equals 2, 7, negative 1, and vector b equals 7, 1, 2, 2, then a dot b equals 2 times 7 plus 7 times 1 plus negative 1 times 2 plus 0 times 2, which equals 14 plus 7 minus 2 plus 0, which equals 19. Therefore, a dot b equals 19. We can use the definition of the dot product to find a geometric interpretation of the dot product. But before we continue, there is one important property of the dot product that we need to understand that will make it easier for us when we go try to find the geometric interpretation of the dot product. This property states that the dot product of a vector with itself equals the magnitude of the vector squared. So u dot u equals the magnitude of the vector u squared. The mathematics behind this statement is fairly simple. Using the definition of the dot product, if we are taking the dot product of a vector with itself, for example u dot u, then that means u dot u equals the sum of ui as I goes from 1 to n, and we could simplify this to ui squared. It may help if we write out this equation in full, like this. Now let's look at what the magnitude of the vector u equals. The magnitude is given by the square root of u1 squared plus u2 squared plus u3 squared, and all the way up to un squared. Therefore, if we square the magnitude, then we get rid of the square root sign. And now we have shown that u dot u does equal to the magnitude of the vector u squared as required. Now let's move on to explore the geometric interpretation of the dot product. First, let's call this vector a and this vector b, and position them so that the tail of each vector is touching. Theta is the angle between a and b. Note that we choose this angle for theta, rather than the other angle, which we can call alpha. To be more mathematical, we can restrict the domain of theta to be between 0 and pi, so theta is either an acute angle or an obtuse angle. We can create a triangle using the vectors a, b, and a minus b. It is important to understand that these letters only represent the names of the vectors, not lengths of each side. To find the length of each side, we would have to take the magnitude of each vector. By cosine rule, we can form an equation relating the lengths of the three sides of the triangle with the angle theta, like this. Before, we just established that the dot product of a vector with itself is equivalent to the magnitude of the vector squared, and therefore that means the magnitude of the vector a minus b squared is equivalent to a minus b dot a minus b. Now we expand the dot product, so we get a dot a minus a dot b minus b dot a plus b dot b. And once again, using the property that the dot product of a vector with itself is equivalent to the magnitude of the vector squared, we can simplify a dot a to magnitude of a squared, and we can also simplify b dot b to magnitude of b squared. And this cancels out, and this also cancels out. Next, we divide both sides by -2, and very nicely, we reach our formula. A dot B equals magnitude of A times magnitude of B times cosine theta. And this is a geometric interpretation of the dot product, which we have proved by using the cosine formula.